For decades, the universe's first stars have been a mystery, hidden in the cosmic dark ages. Now, the James Webb Space Telescope may have finally found them. This discovery could upend everything we thought we knew about the Big Bang, revealing how the earliest light ignited and how the first cosmic structures formed. The eternal darkness before dawn. In November 2025, astronomers made a discovery that sent shockwaves through the scientific community. The James Webb Space Telescope captured something that shouldn't exist, a tiny galaxy called LAP-1b, containing stars so ancient and so chemically pure that they might be the very first stars ever born in our universe. For 60 years, scientists predicted these population 3 stars existed. They searched. They theorized. They built the most expensive telescope in human history specifically to find them. And now, they might finally have proof. This discovery could rewrite everything we know about how the universe began. But before we explain why, you need to understand what the cosmos looked like before any star had ever ignited, a time so dark, so empty, that astronomers gave it a haunting name. Imagine absolute darkness. Not nighttime darkness, true emptiness. For the first few 100 million years after the Big Bang, that's exactly what the universe was. No stars. No galaxies. Nothing but an endless sea of hydrogen and helium gas drifting through infinite black. Scientists call this era the Cosmic Dark Ages, and here's why it matters. During this period, the universe faced a paradox that seemed impossible to solve. To form a star, gas needs to collapse under gravity. But to collapse efficiently, gas needs to cool down. And to cool down, it needs heavy elements, metals, that can radiate heat away. The problem? There were no metals yet. They only get forged inside stars. It's a cosmic chicken and egg problem that baffled physicists for decades. So how did the first stars ever form? The answer shocked astronomers when they figured it out. Without metals to help, the first stars had to form differently. Massive clouds of primordial gas, millions of times the mass of our Sun, slowly contracted over millions of years. The process was brutally inefficient. Tiny fluctuations in density, remnants from the Big Bang itself, provided the initial seeds. Dark matter helped too, its invisible gravity pulling gas into clumps that would eventually become dense enough to ignite. But eventually, somewhere in that dark void, enough gas collapsed to ignite the first nuclear fusion reaction in cosmic history. And when that first star turned on, it didn't flicker to life gently. It exploded into existence with a fury we can barely comprehend. These weren't stars like our Sun. They were monsters 100 times more massive, burning millions of times brighter, and destined to die young in spectacular explosions. The lifespan of these stellar giants was shockingly brief. While our Sun will burn for 10 billion years, population 3 stars exhausted their fuel in just a few million years, a cosmic eye blink. Then they detonated, scattering the first heavy elements across the universe and setting the stage for everything that followed. But here's the twist. Despite 60 years of searching, no one had ever actually seen one. They existed only in equations and computer simulations. Their light should still be traveling toward us from billions of years ago, but finding that light required technology that didn't exist. Until now. The telescope built to find the impossible. Finding population 3 stars wasn't just difficult, many thought it was impossible. These stars burned out billions of years ago. Their light has been traveling across the universe ever since, stretched and dimmed by cosmic expansion until it became nearly invisible. The stretching is key. When the universe expands, it doesn't just push galaxies apart, it stretches the light traveling between them. Light that started as visible or ultraviolet radiation gets pulled into longer wavelengths. After 13 billion years of stretching, that light becomes infrared heat radiation invisible to human eyes and most telescopes. To detect it, we needed something unprecedented. Enter the James Webb Space Telescope, a $20 billion gamble that took 3 decades to build. Why so expensive? Because catching ancient starlight requires catching infrared radiation, heat signatures so faint they're measured in single photons. JWST's mirror spans 6.5 meters, nearly 3 times larger than Hubble's. Its 18 hexagonal gold-plated segments collect light with extraordinary precision. But size alone wasn't enough. The telescope also needed to be cold. Impossibly cold. Here's the problem: infrared is heat radiation. If your telescope is warm, it glows in infrared, drowning out the faint signals you're trying to detect. It's like trying to photograph a firefly while standing next to a bonfire. JWST's 5-layer sunshield keeps the instruments at -233 degrees Celsius, colder than any natural environment in our solar system. When JWST launched on Christmas Day 2021, astronomers held their breath. The deployment involved 344 single point-of-failure mechanisms. If just one failed, the entire mission was dead. Engineers couldn't fix anything. The telescope was headed to a point 1.5 million kilometers from Earth, 4 times farther than the Moon. But somehow, impossibly, every single mechanism worked. The mirror unfolded. The sunshield deployed. The instruments cooled down and powered up. The telescope's first deep-field image, released in July 2022, stunned the world. Thousands of galaxies appeared in a patch of sky you could cover with a grain of sand held at arm's length. Some of those galaxies were shining just 300 million years after the Big Bang, far younger than anyone expected. But that was just the beginning. What JWST found next contradicted everything astronomers thought they knew. A galaxy that shouldn't exist. LAP-1b is weird. Really weird. And astronomers love weird because weird usually means discovery. First, consider where it is. LAP-1b sits 800 million years after the Big Bang, roughly 13 billion light-years away. At that distance, even JWST shouldn't be able to see it. The galaxy is tiny, containing only about 2,700 solar masses of stars. That's not a typo. Our Milky Way contains over 100 billion solar masses. LAP-1b is practically invisible. So how did astronomers spot it? Gravity itself became a lens. Between us and LAP-1b sits a massive galaxy cluster called MACS J0416. This cluster contains trillions of solar masses of ordinary and dark matter. All that mass warps spacetime around it, bending and magnifying light from objects behind it like a cosmic magnifying glass. LAP-1b's light got boosted by a factor of 100. Without this gravitational lensing, the galaxy would be completely undetectable, even to Webb. Think about what that means. We needed humanity's most advanced telescope, operating at the edge of physical possibility, and a trillion solar mass cosmic lens perfectly aligned between us and the target. The odds of this configuration existing are astronomical. We got lucky. But the magnification wasn't even the most shocking part. When astronomers analyzed LAP-1b's spectrum, the fingerprint of light that reveals what something is made of, they found something that made them question their instruments. The stars contained almost no metals. We're talking trace amounts, a tiny fraction of what our sun has. This isn't just unusual. In the modern universe, it's essentially impossible. Every star we've ever studied contains metals forged by previous generations of stars. LAP-1b's stars appear to have formed from pristine, untouched primordial gas that had never been processed through a stellar interior. There's more. The radiation streaming from these stars is extraordinarily hard, meaning it's packed with high-energy ultraviolet photons. Normal stars don't produce radiation this intense. Neither do typical black holes. Only one type of object matches this signature: massive, metal-free population 3 stars burning hydrogen at temperatures we've never directly observed. The smoking gun. Skeptics immediately pushed back. Maybe LAP-1b's stars aren't metal-free, maybe they're just hiding metals somewhere the spectrum can't detect. Maybe the instruments were miscalibrated. Maybe gravitational lensing distorted the data in unexpected ways. Fair questions. Science thrives on skepticism. But the evidence kept piling up, and each new finding pointed in the same direction. The carbon-to-oxygen ratio was wrong. Not just slightly off, dramatically different from any known stellar population. In the modern universe, stars produce carbon and oxygen in predictable proportions based on their internal fusion processes. LAP-1b's ratio matched theoretical predictions for primordial nucleosynthesis, the specific chemical fingerprint expected from the universe's first generation of stars. Then there's the dark matter problem, except in this case, Dark matter isn't a problem. It's a solution. Observations revealed that LAP-1b's visible mass, its stars and gas, represents only a small fraction of its total mass. The rest. Dark matter. Lots of it. The galaxy sits embedded in a dark matter halo far more massive than its visible components suggest. Why does this matter? Because theoretical models predicted exactly this arrangement decades ago.